Today's discussion will focus on the LCMS analysis of oligonucleotides for molecular weight conformation. Let's say you are working with a new oligo lead or a candidate with several modifications or new chemistries and you want to confirm the molecular weight. Basically, ensure what you wanted to synthesize is indeed what you ended up with. So you analyze an oligo on an Agilent LC-MS-DXT, a single quadrupole detector which can scan up to 3000 m/z. Wait, you can do intact mass of an oligo with a single quad? And in most instances, yes, you can. You also want to ensure that you use an LC column packed with pH stable, superficially porous particles to ensure excellent peak shape so that you can extract a spectrum from the main peak. Now with the data analysis, you have an oligo spectrum where multiple charge states are detected. To determine the neutral mass or molecular weight, we need to deconvolute the spectrum, and we don't necessarily want to be wasting time tinkering away with esoteric parameters. And this is where OpenLab CDS 2.8 with spectral deconvolution comes in. Before talking about spectral deconvolution in OpenLab CDS, briefly, why are oligonucleotides seemingly on the fringe of exploding as a therapeutic modality? Recall from high school the central dogma of biology. DNA gets transcribed to mRNA. mRNA then gets translated to proteins, and most drugs work at the protein level. However, if you have a dysfunctional gene, these diseases were untreatable, so-called undruggable targets, because they acted at the gene expression level. With nucleic acid therapeutics, we can bypass the central dogma of biology with therapeutic oligos, either with gene silencing or splice switching. Errant gene expression can be corrected. And yes, there are new modalities in gene therapy, IVT mRNAs, and even gene editing. However, oligos are somewhat more established. Indeed, 2016's blockbuster Spinraza certainly indicated that this was the case. Further, as lipid nanoparticle technologies and conjugation chemistries advance, oligos will only continue to be a more viable therapeutic modality. And with that, a primer on oligos. Oligos are short DNA or RNA oligomers. They bind and can base pair to complementary strands with purines pairing with pyrimidines, forming a helix structure. DNA contains a sugar deoxyribose, while RNA contains a sugar ribose. Additionally, the base thymine is exclusive to DNA, and removal of a methyl gives uracil, exclusive to RNA. Oligos, of course, are importantly negatively charged with a phosphodiester backbone. There are a variety of different types of oligos, primers, dual label probes, etc., but the ones pertinent to today's discussion are the therapeutic oligos. The challenge with therapeutic oligos are the myriad modifications that are introduced to improve both stability and efficacy of the oligos. In short, both hybridization and nuclease resistance can be improved by chemical modifications. This includes the ubiquitous phosphorothioate modification for nuclease resistance. This essentially introduces a sulfur to the standard phosphodiester backbone, but there are others, including the 2' modifications when working with RNA, as well as ribose modifications for improved affinity of binding to complementary strands. There are even nucleoside analogs where we use a completely different backbone. These are unique in that they are not negatively charged, and they can be treated more similarly to peptides, at least from an LCMS perspective. Taking a step back, these chemical modifications can be introduced because oligos are manufactured by solid phase synthesis. Using a CpG as a scaffold, oligos are synthesized in a stepwise fashion from 5' to 3' with phosphoramidites, which are protected nucleosides. However, invariably what occurs during the synthesis are failure sequences or shortmers, the unintended incorporation of nucleotides, or longmers. These are more commonly observed process-related impurities, but due to the amidites having a wide variety of protecting groups, well, different alkylated impurities are also relatively common. And yes, at a certain point, we want to characterize these impurities, but if you're earlier in development or simply need a quick answer, intact mass with a single quad like the LCMSDXT and OpenLab CDS is an excellent choice where speed to answer is prioritized. Now let's quickly talk about LCMS and electrospray ionization for large molecules. As mentioned earlier, large molecules such as proteins and oligos have multiple ionizable moieties, and consequently, during ESI ionization, they can take on several charge states. The resulting is a charge state distribution or charge envelope, typically with a Gaussian distribution. Note this is the same molecule, thus the same molecular weight or M, but with a different number of charges or Z. The subsequent spectrum will then need to be deconvoluted, that is, simplified to the measured mass where Z is equal to 1. This often utilizes high-resolution mass detection, such as a time-of-flight instrument or a Fourier transform ion trap. However, large molecules can most certainly be analyzed with nominal or unit mass detection, like a single quadrupole, including the Agilent Infinity LCMSD series. Before talking about deconvolution in OpenLab CDS, it is prudent to understand deconvolution in general. If you're here for chromatographic deconvolution, I apologize profusely. I've probably bored you to death with talk on large molecules. This is spectral deconvolution, or the simplification of the charge envelope observed with large molecules. So recall, mass spectra are a plot of mass divided by charge, and for small molecules, Z values are typically 1, maybe 2, but with large molecules, we have the multiply charge, and so spectral deconvolution must be performed. Deconvolution is just the mathematical process of simplifying the large molecule M over Z spectrum obtained by LCMS and determining the neutral mass. Many different types of MS and CDS softwares employ different algorithms. Sometimes this is proprietary. And although there are some user-defined parameters, a lot of this is a little bit of black magic. The most common type of mathematical model or algorithm used for deconvolution is max-ent, or the maximum entropy algorithm. This essentially will take the raw spectrum and determine what would be the most probable parent mass distribution, making assumptions on noise. One way to think about it, deconvolution basically takes the spectral data images and sharpens them based on complicated maths. If you've ever used a max-ent tool with your informatics software, you've likely selected a mass range, a theoretical target mass, fiddled with some resolution settings, and got a result. Conversely, MS spectral deconvolution in OpenLab CDS uses a completely different algorithm. It was initially developed as part of ChemStation as a way to determine the neutral mass of triply charged peptides. However, it can also work on many other molecules, including oligos. It can even work on small proteins. Shown here is equine myoglobin at about 17 kilodalton or so. The MS spectral deconvolution in OpenLab CDS identifies components with a charged state based upon user inputted criteria. Then a curve fitting or weighted average is applied to determine the neutral mass depending on which you select. Importantly, unlike max-ent, no images are generated and residual data is retained for further optimization of deconvolution parameters. Additionally, there is no theoretical upper or lower mass limitation. Effectively, the limiting factor is the mass range of the single quadrupole detector that is being used. Again, deconvolution used with many software platforms can be somewhat esoteric to the end user, but in OpenLab CDS, we are very transparent about the algorithm. And really, the math is quite simple. It doesn't need to be overly complex, given we are using unit mass detection. Step by step, here is how the process works. First, an ion list is generated. Low charge states are applied. If isotopes are detected, they are considered. Otherwise, once a theoretical charge state in the ion list matches the user input, the algorithm then looks for the next plus or minus charge state, and the process repeats until the ion list is exhausted. Due to its simplicity and the fact that this was optimized for unit mass detection, this algorithm is most appropriate for molecular weight confirmation or identity workflows. That is, you kind of know what you're looking for already. Now, I won't go extensively into OpenLab CDS for this webinar, though as a longtime ChemStation user, I've grown quite accustomed, I've grown quite fond of OpenLab CDS. However, briefly, spectral deconvolution in OpenLab CDS has its own specific method, which enables a new layout. Within the layout itself, one can easily view chromatograms, both UV and total ion current, and extract spectrum either manually or automatically, depending on the processing method parameters. Speaking of which, processing method parameters are relatively straightforward. Simply set the negative and positive mode, set the M/Z range, and target molecular weights, as well as the number of charge states in the envelope. Advanced settings are available to set noise thresholds and how Gaussian the charge envelope is. And this is a webinar, not a software tutorial. I could go into the software and show you it, but really that doesn't translate quite well in a webinar. So if you want to see this CDS tutorial, simply go to the URL that is highlighted in the bottom right. Once the processing method parameters are optimized, one can implement the unattended workflow. The saved optimized processing method is assigned in the sequence during acquisition. So after the analytical LCMS run, the data analysis will automatically process the data. The data may then be reviewed as needed. Then the user can print the report or simply copy the deconvolution results from the results table, whichever is appropriate for a given workflow. Now, let's talk a little bit about the use case of oligos in OpenLab CDS using the LC MSDXC, at least in this example. First, from an LC perspective, the column is superficially porous, but chemically modified for stability under harsh conditions that are used for IPRPLC. 50 millimeters is sufficiently long for oligos due to the mainly adsorptive separation that is used in ion pair reversed phase. Also notice super hot temperatures, 65 degrees, safe for these types of silicas that are chemically modified, such as the advanced biooligo and indeed denaturing methods for duplex oligos. For example, sometimes the temperature may exceed that. As far as the LCMSD is concerned, AJS tends to do well for oligos, though standard ESI also fares well. Gas temp is between 275 and 325. Here we have shown 300. Negative mode for oligos, obviously optimize a fragmenter voltage for sensitivity, though be wary of in-source fragmentation. Most commonly, depurination will be observed. Finally, one note for spectral deconvolution in OpenLab CDS, data collection prerequisite is full scan profile. Deconvolution will actually not work with centroided data. And it took a while, but here, finally, some data. Oligos and peptides, to a large degree, differ somewhat in the expected charge envelope that might be observed. This is highly dependent on the source settings as well as the mobile phase used. Briefly, ESI desorption of oligos is complicated and can appear somewhat unpredictable and counterintuitive at first. For example, here is a comparison of the mass spectrum of a 15-mer DNA oligo on the top and 40-mer DNA oligo on bottom. This is from the Agilent poly-DT ladder. Longer oligos generally have higher charge states with broad charge state distributions, though again, this will depend on the mobile phase and the source settings. And as such, if working with many different types of oligos, that is different lengths and different modifications like conjugations and such, that would result in either large molecular weight or somehow differences in charge envelope, deconvolution settings should be optimized. Shown to the right are standard deconvolution settings that cover this wide range of different lengths of oligos. The results that should be expected from spectral deconvolution in OpenLab CDS, well, provided the LC and MS methods are robust, the deconvoluted or measured mass percent RSDs will be quite reproducible. Note the delta masses for each of the poly-DT standards all range between 2 and 5 or so Dalton. With unit mass, it's a bit of a misnomer to report mass accuracy to the deconvoluted neutral mass. Another approach might be to just look at the delta M over Z between different ion sets in theoretical charge envelopes, and these will be between 0.2 to 0.5 M over Z with some very good consistency provided instruments are tuned and maintained. In either case, these are the results that one can expect, and if anything is wildly off, retention times of peaks of interest or calculated masses for deconvolution are somewhat off, troubleshooting should then take place appropriately. Optimizing deconvolution settings is somewhat trivial relative to the optimization of the LC and MS settings themselves. Further, one can use the same analytical method, so same LC, MS, and deconvolution settings for molecular weight conformation of a fully thioated single-stranded oligo with 2' MOE modification, FOP sequence shown on the bottom left. Again, same deconvolution settings and calculated mass and experimental mass are very close. 0.2 delta mass in Daltons or 36 ppm, which I'm stating here because 36 ppm is pretty good for unit mass. And it fits my narrative. Again, I tend to compare the theoretical M over Z to the measured M over Z, but whatever floats your boat. In either case, single quads are robust and excellent for molecular weight conformation, though you should not expect to have the same mass accuracy of a TOF. However, there may be instances where one will need to perform some investigative workflows. In other words, you need to go back into open lab data analysis to review some data after some unexpected results. So here we look at another thioated oligo and a putative N-1 peak being unacceptably or unexpectedly high. With the molecular weight range being somewhat too broad in the previous example, here we actually have to adjust that to the molecular weight range shown here as 6,000 to 8,000. This slight adjustment is needed to confirm that indeed the extracted spectrum from pre-peak indicates that it is in N-1. And if this was a super big deal, one could go back and analyze that same sample with a TOF or QTOF, but here we are simply demonstrating that for investigative workflows, or simply when you need to optimize the deconvolution settings for more fidelity, adjusting the low and high molecular weights might be necessary.